All right. So we have talked about temperatures. We've talked about pressure. We've talked about moisture and related them to different aspects of the weather. Well, we're bringing it kind of all together here. If you think about it, when you're trying to forecast the weather, you want to know what is happening to an individual air parcel as it moves to some future point. So wind is what moves that air parcel. The changes that go on in that air parcel are such things as what control temperature, what control the amount of moisture into it, what even controls the pressure, which can influence where the air parcel is going. So this week we're going to talk about wind. So with that, what forces control the speed and direction of the wind? Wind is just local motion of the air. In other words, if you walk outside, what you feel blowing in your face or at your back, pushing you somewhere, is the wind. You can't really see it. You can see what it does. You can feel it. So there's always a pressure, it's a push or pull that's pushing this wind. So there must be some kind of force that's being applied to make an air parcel move. Newton said that anything that's going to move has to have some kind of force that's causing it to move in some direction. And the force is equal to the mass times an acceleration. That acceleration may be gravity. That acceleration may be other aspects. And we're going to look at all those that deal with air parcels. So we talk about air pressure gradient, centripetal force, Coriolis effect, friction, gravity. So let's go into delve. The pressure gradient force is one that you've seen on the maps all the time. The closer the isobars together, the more there's a slope there of the air, the faster the air is going to want to move. And remember, air is always going to move down from higher pressure towards lower pressure. So that is the way the force will act. So the tighter the gradient, the faster the winds are going to move. The further apart the lines are, particularly in high pressure systems, the lines get pretty far apart. But in low pressure systems, they can get pretty tight, right next to each other. So when you look at a weather map, if you're interested in the wind, one of the very first things you're going to look at is the pressure gradient. How much close together are the lines? Another aspect of it is centripetal force. Centripetal force is a force where it keeps an object moving in a circle. If you go around a curve in a car, what keeps you on that curve instead of going straight through it and right across and out into space? Well, what that force is called centripetal force. It's directed in towards where the curve, keeping you in line around it. Or if you, in this case, you have a ball flowing around, the centripetal force is on that string. If you cut that string, that ball is going to go in a straight line somewhere. So then this hammer thrower lets go of that ball. That ball is going to all of a sudden not have any more force, centripetal force there, and it's going to move outward, straight in a straight line, because that's the way the force would be directed. So when you're looking at winds around the low pressure system, where the winds blow in a circle, or a high pressure system, centripetal force is what's working there to keep those winds blowing in that direction. And it's not independent. It must be because there's something is pulling it around. There's another force. It only occurs on a rotating Earth, like ours. If you looked at the U.S., say you have a point right here in the middle of the United States, and you looked at it several hours later, well, what would happen is, think about it, the North Pole isn't moving that much at all. However, the equator is moving pretty quickly to go all the way around. So the closer you are to the equator, the faster the pull is to push whatever that part of the Earth is in a different direction. And you can see here it actually acts to the right in the northern hemisphere. In the southern hemisphere, it acts to the left. But we're going to deal with northern. So it pulls any object that's moving to the right. It occurs stronger the further north you are. So the closer you are to the North Pole, the stronger that force is. If you get down to the equator, that force doesn't exist anymore. So you can see here the deflections. See, they all occur if you have pressure gradient pulling you up towards 60 degrees. Remember, it's low pressure at 60 degrees north, high pressure around 30. So we would have winds that tend to curve to the right. When you get down closer to the equator, they don't have as much. And down here in the southern hemisphere, they tend to curve to the left. Friction is another force. Think about it. If you have wind flowing over a mountain, that mountain's going to be trying to block that wind. It's going to cause it very difficult for that wind to go up and then down over it. So there's a lot of friction there. Further up in the atmosphere, there's less friction, but there is friction all the way up because air molecules are moving against each other. So there's always some friction. Friction is extremely difficult to explain. And the turbulence it generates and fluid flow. One of the things they did demonstration when I was taking a class in turbulence and dropped a creamer, one small drop of creamer into a cup of coffee. The creamer hits the coffee and moves in all different directions if you see it. That's turbulence. So try explaining that. It's pretty complicated. That's why we don't do a really good job with it yet. Gravity is another force. Everything on the earth is pulled down towards gravity. And in the earth's case, obviously gravity holds two things. We have a rotating earth, so we have a pull downward, and because it's rotating, there's another pull inward, keeping that object on the earth. The two work together to make what is gravity for Earth. And that works out to be 9.8 meters per second of an acceleration. So that can be part of a force. So now we've looked at horizontal pressure gradient, centripetal force, Coriolis effect, friction, and gravity. Each one of these is what causes air particles to move. So let's just look at the simple one. Start up and down. All right, we've talked about pressure dropping very quickly in the vertical, especially if it's very cold where you are, the pressure will go up even faster. Think about it. 850 millibars many times is right around, 5,000 feet? So if it's around 5,000 feet, not even a mile, you have dropped pressure from standard, right around 1,000 millibars, to 850, 150. So in not even a mile in the vertical, you have dropped pressure 150 millibars. Go walk between Beckley and Charleston on a very windy day, and you might only drop the pressure 15 to 20 millibars. Think about the difference. So there is a tremendous pressure gradient in the vertical that's not there. There's some in the horizontal, but nothing like the vertical. So why then doesn't the atmosphere all collapse down? Because we say the atmosphere will go towards low pressure, so it all should just leave the earth, right? Well, gravity. Gravity pulls those air parcels down. And the balance, an air parcel does not move because gravity and that pressure gradient are balanced. That's called hydrostatic equilibrium. It is what keeps that air parcel right in one spot. Parcels can move. They could be pushed up a mountain, for example, or maybe winds underneath them are lifting upwards over a warm front or a cold front. So they can push it up, but it's all going to be moving at the same speed if it's under hydrostatic equilibrium. There's another wind type called geostrophic wind. What happens here is the pressure gradient and the Coriolis effect are balanced. What that means is They're the only two effects right now going on. So you have a wind going in a straight line that is balanced, where the Coriolis effect, which is acting to the right of the wind, is balancing the pressure gradient effect. Now you have the gradient wind. Oh yeah, we're going to add something else in here. We're going to add a centripetal force in here. So you have the Coriolis effect, you also have the pressure gradient, and you have the centripetal force. And that centripetal force is always changing, and it's what causes it to go in a circle. So the gradient wind will go clockwise or counterclockwise, depending on which low or high pressure. Friction as another component. Friction just slows the wind. Doesn't work on anything else. So if you have wind, and they show it right here as a wind, friction is always going to be the opposite, pushing away from that wind direction, that force. So if that happens and the wind slows, pressure gradient doesn't change, but the Coriolis force does. It becomes weaker, so it's not pushing as much to the right. That means that when you're looking at pressure around the low pressure system on the surface, where the friction is the greatest, it's going to allow winds to tend to converge into this low pressure. And you can see that depicted right here. All right, the wind is all the air is working together. So if you have horizontal convergence aloft, well, then that wind's going to be pushed together. It's got somewhere it's got to go, so it's going to try to sink down to the Earth's surface. It hits the Earth's surface, and what happens? It spreads out. You wind up with divergence. So when you have convergence aloft, you typically have divergence and sinking air. Now you go the other way. If you have horizontal divergence aloft, air from below it's going to tend to rise, go up, and you wind up with vertical motion. So you can look here and see when the winds are going through a smooth surface. For example, if a rough surface, they're going slower. They're going to pick up speed over the lake when they hit it. If they do that, there's going to be divergence because the winds picked up speed. And divergence at the surface means winds are going to converge aloft, winds are going to sink. Now, on the other end of it, at the lake, if the winds are coming from the lake and hit the land, the winds are going to slow. You're going to see this in a question this week. If the winds are slowing, there's convergence taking place. The air has got to go upwards. This happens on the south side of the Great Lakes in the winter when there's a northwest wind, or when it hits the mountains in West Virginia. The wind slows as it comes to the mountains. Can't go right up, but it rises up because of the convergence and the help from the mountains. That's why you get a lot of the snowfalls in the wintertime. So with that, let's just take a quick peek at a couple winds. Here's today's weather map in the surface wind. Notice the pressure gradient here. Fairly strong around the low pressure. The winds are blowing in towards the low pressure and out of the high pressure, working just like we talked about. If you go aloft up to 300 millibars, what you see is winds parallel to the isobars, and you wind up with geostrophic wind. 850 millibars, you're kind of in a mixed area. So you're starting to get some friction playing, so you might move some air towards it. And notice the gradient wind here around the low pressure right here in a circle. So the gradient wind there, or right around the curve here as it goes around the curve, and then gradient wind. So you can depict at any level, and you can see how the wind's moving due to the forces. And then how that air parcel is changing due to all the other stuff. And that's how the weather forecast winds up being made. So I hope you got a little bit out of this, and let me know if you have any questions.